Okay, so in the other video, we stopped right at the point where we built the model, and so we have our differential equation there. And before I go any further, I just wanted to talk about how to deal with that spring constant, since this is really usually the thing we need to find in the story problems. And so let's try a few examples. I'm going to pause while I write down the problem. Okay, so a spring with mass 2 kilograms has a natural length of 0.5 meters. A force of 25.6 newtons is required to stretch the spring to 0.7 meters, and so we want to find the spring constant. Okay, so how are we going to do that? Well, we know that the force is proportional to the length, right, that the spring is stretched. And so therefore, the force, which is 25.6, is proportional to, that's our k times our length, and our length is 0.2. Right, so k is our spring constant, which is also the constant of proportionality. And so therefore, in this case, we just take k equals 25.6 divided by 0.2. And if you compute that, you get 128. Good. Alright, so that's kind of the first type of model that you might see, where we just give you the mass and the spring, or the length that the mass has taken the spring. We'll try another one. I will pause again while I write down the question. Okay, and so in this example we have a mass weighing 10 pounds stretches a spring 2 inches. What is the spring constant? So kind of implied here, right, is that the spring, the 2 inches, is how much it takes to get to equilibrium. And so we have to be a little bit concerned here with the units. Number one is, if we're working with pounds, we should be working with feet. And so we'll take 2 inches to be 1/6 feet, just for units. And also, we might note that force, or pounds I should say, pounds is a force. In other words, 10 is equal to mg, right? So with those two statements here, can we figure out what to do? Well, if we're at equilibrium, then the force down is equal to the resistance or restorative force up, right? And so that means that mg is equal to kl, or you might notice that we said before that mg minus kl was equal to 0 at equilibrium, right? And where L is the extra length that the spring is stretched. So just plugging in our numbers then, we have 10 equals k times our 1/6, and so that means in this case that k is equal to 60. Good. I'll pause again and write down the next question. Alright, so our next example is that a spring is stretched 0.1 meters by a force of 3 newtons. A mass of 2 kilograms is hung from the spring, excuse me, which is attached to a viscous damper that exerts a force of 3 newtons when the velocity is 5 meters per second. So write the differential equation that models the displacement of the mass, u of t. Alright, so we've got a couple things going on here in this one. We have the spring constant, and we have the constant for the damping factor. So let's focus on the spring constant first. Spring constant. So it sounds like we're not really told about the how much mass requires the stretching, or takes on the stretching. We're just given the stretching and a force, right? So that just says that k times 1/10 is equal to 3, and so therefore just k equals 30. That's pretty straightforward. Good. We also notice that the mass is going to be 2 kilograms. And so finally, the viscous damper, what is that? So if I have like a mass on a spring, right? I need my mass to kind of come out here, because I need something else to kind of hold on to it. So this is something of a viscous damper. So this would the purpose of this damper then is to cancel out the spring action, right? So to slow it down, and so that's why we're talking. That's how we're giving this force of 3 newtons. Okay, now our assumption is that that force is proportional to the velocity, right? And so that's why we're also given the velocity. So we know that 3 is proportional to the force, or the velocity. Oh gosh, I need a little coffee. So therefore, k is equal to 3/5. Oops, sorry. Let's not use k. We were using gamma before. And so gamma is 3/5. Good. And so now we have our 3 constants. We have our m and our k and our gamma, and so therefore the differential equation is given by 2u double prime plus 3/5 times u prime plus 30 times u equals 0. Good. And it's equal to 0 because we have no external forcing yet, right? Very good. Okay, I'm going to pause here while we change gears a bit, and I'll be back in a sec. Okay, so we finished up our model last time, and now we want to talk about some general properties. So we're going to be talking about the general model with no forcing. Okay, so our first even more specific example is what happens if you have no forcing, and no damping. And that means your differential equation just looks like mu double prime plus k times u equals 0. And so putting in our characteristic equation, we see that r squared is minus k over m. And by the way, our constants are all positive here, right? M and k are positive. Okay, and so therefore r is plus or minus the square root of k over m times I, and so therefore the solution is going to be u of t equals a cosine of the square root of k over m times t plus b times the sine of the square root of k over m times t. Right? And we know that we could rewrite this as r times the cosine of the square root of k over m times t minus some delta, where we have to compute the r and the delta. Well, in fact, maybe I should write those down. R is equal to the square root of a squared plus b squared, and delta is, you can think of it as the, oh boy, that was loud, argument of a plus ib, or you can think of it as the 4-quadrant inverse tangent of b over a. Okay, but the main point I wanted to make here was that the period, this is periodic, this is periodic. With period, can you read off the period? It's 2 pi divided by the square root of k over m. Okay, good. All right. So with no forcing and no damping again, our solution just oscillates back and forth. Never dies off. All right. Now by adding in damping, I think we're on case B now, right? Oops, sorry about that. Add in damping. Right, and now we have our normal model, mu double prime plus gamma u prime plus k times u equals 0. And so we can solve our characteristic equation, minus gamma plus or minus the square root, gamma squared minus 4mk, all divided by 2m. Good. And so what happens from here is, remember, we have 3 cases, depending on if the discriminant is positive, negative, or 0. And so Case 1 would be where gamma squared minus 4mk is greater than 0, and then we have two real roots to that. In fact, it can be shown, whoops, it can be shown that the two roots, R1 and R2, are both negative. I'm going to let you think about that. And so this is the case where we're going to say that the system is said to be overdamped. Okay. Second case is where the discriminant is less than 0, and so that's going to give us complex roots. And things still die off. I think you can probably see that in the solutions to the characteristic equation there. But in this case, we're going to say that the system is underdamped. And in this case, we're going to see that we get oscillations that are dying off. Okay, and in the last case, we might guess, oh, that's gamma squared, not r. 4mk equals 0. And this is kind of the critical piece, right, because it separates over from under damping. We have critically damped. And so these are just some vocabulary words that we're going to use to describe these three cases. Okay. Now remember, underdamped is where we still have oscillations, but they're dying off. Oscillations dying off. Getting smaller. Overdamped, we have no oscillations. Although it may cross the x-axis or t-axis once, it's not going to cross twice. And critically damped is things are just moving. There's no oscillations there either. And I should say that if you were to look at a picture, it's kind of hard to distinguish between the overdamped and the critically damped case because they're so close. So graphically, we're not going to try to distinguish between those two, but we should be able to distinguish between overdamped and underdamped because that's, the oscillations are a dead giveaway of what's happening. Good. So we're going to take a look at those in the next video, where we might look at a few examples.